Now, a lot of the time, the way that NP-hard problems get talked about is as if you can't solve them. Well, probably not in worst case polynomial time on a deterministic Turing machine, sure. But exponential time is not like forbidden, it's just a lot. Computers are pretty fast though, and sometimes the instances that you want to solve aren't that large anyway. Depending on both the problem and the methods, you can actually solve larger instances than you might expect. You can do independent set with hundreds of vertices, no problem. Under some circumstances, you can do knapsack with millions of items in less than a minute. And then, of course, there are heuristics and approximation algorithms, which are also massively relevant in practice, but I'll focus on coloring inside the lines here. Let's actually solve the problem as stated. First of all, there is a humongous difference between n factorial and 2 to the n. Brute forcing a permutation stops being fun after about 10 or 12, but 2 to the n time gets you up to about 30 quite comfortably if the constant factors are low. And luckily, a lot of the time you can actually use dynamic programming to get permutation problems down to 2 to the n time at a cost of space. Take a look at the held Karp algorithm for traveling salesmen, for example. Then there is so-called solver software, especially for SAT and ILP. These are sophisticated pieces of software for satisfiability and integer linear programs. You may recognize that both of these problems are NP-hard themselves, but there is a lot of algorithmic and practical knowledge in these specific solvers, as well as years or even decades of software engineering and tuning. So it actually tends to work out quite well to reduce your problem to satisfiability or to ILP. Some of these solvers are commercial, but they tend to have free academic licenses for students and staff. Just to throw some names out there, Cplex, Gurobi, and Skip for linear programs, and Minisat and Cadical for satisfiability. But especially for SAT, there are many options with particular strengths, so be sure to shop around. Next, there's the concept of moderately exponential time algorithms. That's actually an entire field of study. NP-hardness does not mean that the only solution is brute force. For example, it's fairly easy to do independent set, in worst case about 1.7 to the n. And that's an exponential improvement over the trivial 2 to the n. You can actually do much better still, and I'm sure we'll talk about that some other time. My point here is that polynomial time algorithms aren't the only place where you get to be smart, and in some sense, it matters even more here. Finally, for today, there is the concept of fixed parameter tractability, FPT, which is kind of a way to formalize that the number of vertices or the input length or whatever may not be what really matters. There is an algorithm for deciding k vertex cover, for example, with runtime of 2 to the k times n. For fixed k, that's linear time on this NP-hard problem. Now, of course, k could be linear in n, and then it is exponential, but it tells us something about what makes an instance hard. And it's not necessarily the size of the graph. If you're only going to get instances with low k, or if you only care about the result if k is low, this is a really interesting framework. It's a little bit more subtle than I've let on, but you can look that up if you need to. Some more keywords here are kernelization and fine-grained complexity. So yeah, NP-hard does not mean that you can't solve it.